Hello, I'm Matthew, and this presentation is on demand control ventilation energy savings for air handling units. So the goal is to determine the potential for energy savings for air handling units using integrated systems and demand-based controlled. We want to analyze the sensors that are required to do this the most effectively and analyze the sensitivity requirement and the number of sensors that will be required to give building operators the best resolution of data to model the air handling unit and understand its energy consumption historically and in real time. So the idea is that you have the energy usage of the air handling unit, and then you have the demand on that unit, which is some occupants and predicting the occupancy from some CO2 data and understanding the various components and variables that formulate the relationship between energy and occupancy. So for this case study, we used IUPUI lecture hall, and we used the zone controlled by air handling unit number 2. That's the zone highlighted in yellow. And this consisted of 3 lecture halls, which have a total sum capacity of about 734 people. The air handling unit that controls this zone has hot water and chill water coil-based control. So for data collection, we used various different types of sensors. Some of them were sensors that we installed individually, and then others were the building automation sensors that are already in place and able to collect data historically. For the sensors that we install, we used an integrated system, which allows us to put a sensor or even a control on site and to acquire data through that sensor. The sensor communicates with a data collection system, and where the data can be pre-processed to a certain degree, things like sample rate, and can be selected, and then after the sensor communicates with the collection system on site, it sends the data remotely to a database. Here, the data can be stored historically, and the data can be retrieved from this database. You can upload data to the database as well. And then the other thing is this database could be used to communicate with a website or an application where the data is analyzed or visualized in real time, possibly, and could be used for visualization and decision making in real time. So for the lecture rooms, we had various different, we had a specific strategy to lay out several different sensors to collect CO2 data, so that this data can be analyzed to understand the sensitivity to CO2 that these sensors have, and how many sensors would be required to give building operators the best prediction of occupancy to control the air handling unit. So these sensors, you can see from this figure on the right, these blue boxes represent the CO2 sensors that we installed, and then like these green boxes represent the integrated system, which collects the data and sends it remotely to the database, where it can be accessed. All this data can be accessed offsite, analyzed, or even saw in real time. So specifically for the CO2 sensors in sensitivity study, we use this Honeywell model, which has a range of 0 to 2,000 parts per million CO2, kind of well within the range of what would be expected in an occupied building for CO2. This is a diffusion sampling sensor using non-dispersive infrared. And so looking at our data collected from the CO2 sensors, we have our first lecture room here, LE100. This is the mid-sized room for the zone. It has an occupancy of 214 people. We had 2 CO2 sensors, which we're looking at the data for here over trend data for over a week at the sampling interval about 5 minutes. A couple things to note here. These sensors proximity to each other is about 50 feet apart, and they're both wall mounted. We can see that from the data, their average concentration of CO2 that they're seeing is relatively similar, and we can also observe that from the graph that these sensors relatively follow a same trend. And then looking at this data a little deeper for LE100, we see that the CO2 sensed by sensor 1 versus sensor 2 has a relatively good relationship, a stronger correlation of 0.72. So what one CO2 sensor sees, the other relatively sees as well. It sees there's a relationship between the CO2 throughout the room. However, looking at the changes in CO2, we have a relatively weak to no relationship at all between what change in CO2 one sensor sees in one part of the classroom versus what the other CO2 sensor sees and change of CO2 in the other part of the classroom. So looking at our next lecture room, we have LE101. This is the largest lecture hall in the zone controlled by the air handling unit. Has a maximum occupancy of 425 people. And then again, kind of noting the proximity, these blue boxes are the CO2 sensors. These sensors have a proximity of about 35 feet. So a little closer than the last classroom, even though the classroom's bigger. However, the location of the sensors, the elevation is different. One is mounted on a wall, one is mounted on the back of a riser, relatively low. And then looking at the trend data, we see this kind of discrepancy in the magnitude of the CO2 that's being sensed by each sensor. We see kind of they follow, they roughly follow the same trends. We see this peak here, and they both kind of peak out at the same time. However, when it comes to averaging their concentration, it's very poor relative CO2 concentration that they're seeing. And then looking at the trend data, of course, we see this in the correlation between the CO2 being sensed by each sensor. It's relatively weak correlation. There's not much of a similarity or a relationship between the CO2 and one sensor seen versus the other. However, interestingly enough, compared to the last classroom, we see kind of a slight improvement, even though there's still really no relationship between the changes in CO2 that the sensors are seeing. We do kind of see an improvement in the changes of CO2 and that the relationship between what one sensor is seeing and the other sensor is seeing. And then moving on to the last classroom, LE105. This is the smallest classroom in lecture hall, where the lecture hall zone that we're analyzing. And we see here, again, the figure, the blue boxes, the sensors, and their proximity is relatively similar to the last classroom, LE101. It's about 35 feet. And then both are mounted on the wall. And so both have a relative same kind of relationship to occupancy height. And then the thing we see is the trend data over the week. This data has a very similar trend between the two sensors. We can even see that in the average concentration over the time interval that the data was collected. They both have very similar average concentration. Then looking at their correlation data, we have very, very strong relationship between what one CO2 sensor is seen in one part of the room and the CO2 being seen in the other part of the room by the other sensor. And then, although still not considered a strong correlation. We're getting close to a strong correlation. And the change in CO2 that one sensor is seeing in one part of the classroom and the relationship to the other CO2 sensor, sensing change in CO2. This is very interesting that the smallest classroom sees the greatest improvement. And so kind of to observe and conclude what we see from the CO2 data as far as what the sensitivity is and what would be the best amount of sensors for building operators to have installed when they're trying to do demand controlled ventilation for CO2. We see kind of that for the smaller classrooms, LE100 and LE105, we have a better correlation in the CO2 readings as far as what each sensor is seeing. And then interestingly enough, this is not reflected in the change in CO2 with respect to time. But however, I think what's interesting is when the sensor proximity gets closer, the correlation and the change of CO2 is better. So I think it's worth noting that determining the number of CO2 sensors needed to best control based on occupancy predicted from CO2, that would be kind of a variable thing depending on the lecture hall size, where you could mount the CO2 sensors, and then if you had to have multiple sensors, kind of how you would displace those and understand the relationship between those sensors. So moving on to the air handling units, we had sensors that we installed to analyze various trends there as well, and to show the integrated system and the capability of collecting data through the integrated system and sending it to a database where it can be pulled in real time or analyzed historically, and used to make decisions. Here we have some baseline historical data from this, the different sensors some of the different sensors that we use to analyze data. And you can see that kind of the historical trends, there's a lot of information that can be taken away from this to help building operators understand how the air handling unit is operating over time, and to use this data to understand relationships between different variables that tie into the energy of the air handling unit, and to use this to build models that could be used to analyze the data in real time. So in conclusion, we had the sensitivity study of the sensors in the lecture rooms and showed kind of the importance of the CO2 sensors and the number of them and how you mount them, where you mount them, and then using the integrated systems overall to collect data and historically analyze it and model based on that is very important to the future of building operators using data-based demand-controlled ventilation strategies. So thank you for your time. Thank you for listening.